Okay, I'm testing out that the people joining us on Teams can hear me. Can you guys hear me okay? Excellent. Let's get the projector going here. There we go. Would somebody who's on Teams be willing to just unmute themselves for just a second and say hi so I can make sure I can hear you?
Can you hear me?
Yeah, let me turn my volume up a little. Can you say that again?
Is that better? Can you hear me?
Yeah, so I can hear you. Say it one more time.
Can you hear me?
Perfect. Okay, thank you.
No.
Okay, we're going to get started in just a minute. Using more technology than I have at the same time in a long time. So we've got the projector, we've got our Teams meeting, and we are recording. Let me just type something in the chat here. Well, I guess you guys can hear me on the Teams meeting. So if you have a question, you can ask it in the chat, but I might not see it for a minute. So if that's the case, just unmute yourself and speak up, and I'll be able to hear you through my iPad. Okay, any questions from you guys in the audience or the virtual audience before we get started with some announcements? You should be seeing my screen now on Teams. Okay, so a couple of announcements. The first one, we have exam 1 on Friday. So hopefully you are starting to feel prepared for that. It's going to cover everything up to what we do today. So we're certainly not going to finish 1.5 today, but we will hit a couple topics. And then after class, I will list some suggested homework on the website, depending on how far we get. Yeah, let me see if I can make myself louder somehow. Nope, sorry, bear with me for a second. Is that any better, or is that the same? Okay, maybe it's totally broken. Hang on a second. Is there a microphone here I can plug in? Okay, I'm going to try to talk as loud as I can. Hopefully it's not too loud for the people here, and hopefully the people on Teams can hear me. For the people on Teams, I also turned on captions. That might be something you need to turn on your own. If you click the 3 dots at the top, you can click turn on live captions, and it should automatically caption what I'm saying pretty okay and pretty close to when I'm saying it. So hopefully that helps a little bit. Okay, so I was saying exam 1 on Friday. I'll post suggested homework from 1.5 when I get back to my office. That will be just on what we covered. Now, another resource that you can use when studying if you want is if you look on my website and you click on past courses at the top. I've taught this class 3 times before, and I posted exams and homework assignments for those on those websites. So you can go look at those exams and those solutions if you want to, but you have to keep in mind that every semester is on a slightly different schedule. So that exam 1 for the different courses will have material that we haven't covered yet. So it doesn't necessarily mean every question on those assignments you should know how to do, but if you see a question that looks like questions we've done, you can at least use that for practice. Any questions about exam 1 on Friday? Okay. So we'll be taking that, for those of you who are here, we'll be taking that in person for the full 50 minutes. And for those who are not able to join us and are on Teams, we'll coordinate that individually. You can check your email. The second announcement is that grades for homework 1 are posted. I finished that up this morning. I had the biggest fight with technology that I've had in about 10 years trying to get that all to work between D2L and my iPad and everything, but I think I did. So you should see your grade in the grade book. That part is fine. You should also see somewhere on your Dropbox page a PDF that may have the word annotated in the file name, which is all of the comments that I wrote. So I wrote all over your homework and uploaded that. I don't know exactly what you guys see on your side. It's impossible for me to see the student view of a Dropbox. So if you guys could take a look and maybe somebody could post in the Teams page, like, hey, this is where we find the annotated version. That way the rest of you know, and that way I know so I can tell people in the future where you see that file. If you don't see it somewhere, definitely let me know so we can figure that out. And I'm still trying a couple different things with grading, but hopefully we'll get it smoothed out soon. Any questions about that? Okay, hopefully you guys in the Teams chat are doing okay. Let's jump into 1.4. We almost finished that last class. We had just about 1 page of notes left. So we're going to wrap that up and then move on to 1.5. The last thing that we were saying at the end of last class was that the order of quantifiers matters. And so we had an example. I won't go all the way through it, but the example involved the set S of students in this class and the set F of all foods. And the two versions that we looked at were the following two quantified predicates. Let me define, I forgot to define my predicate here. So let me move this out of the way. Our predicate takes in two variables, a student, lowercase s, and a food, lowercase f. And the predicate is the favorite food of student S is F. And so the first version was for all students, there exists a food that is their favorite. And the second version was there exists a food such that for all students, it's their favorite. And we spent a while talking about this, and I told you if it didn't click yet, go home and try to stare at it, read the book until it clicks, because this is important. If this doesn't click, it means you don't fully understand quantifiers yet. So this is a good way to check whether you do. The first version says something kind of like every student has a favorite food. But that means that it could be a different food for each student. It could be a pizza for somebody. It could be a cheeseburger for somebody else. It just says everybody has a favorite food. The second version, though, says something really different. The second version says there exists one food that is the favorite for all students. So the second version says all students in this class have the same favorite food, which is definitely different. So I want to show you another example today that's more mathy. Sometimes the English version clicks more for some people. Sometimes it's the math version. So here's a new example. The first version is going to say for all r in the real numbers, there exists some s in the real numbers such that r plus s equals 0. So I want to break this down and figure out if it's true or false before we write it the other way. So this says for any real number, so if you give me any real number r, I can come up with some real number s such that if I add your number to my number, I get 0. So one way that's useful to think about these is like somebody is giving you the number and they're challenging you. So you're challenging me with some number r, and I have to come back with some s. Then when you add them, they get 0. Does anybody want to say whether they think this is true or false? Yeah, go ahead, Tony. Tony believes this is true, and I agree. For example, if you gave me the number 7, what number would I give back to you? -7. If you give me any number r, I can just come up with the negative version, or if you give me 0, I'll give you back 0. That makes this work. So that's what this says. You give me any number, I can come up with some other number that adds up to 0. Are there any questions about that? Okay, so this is true. What I want to do now is reverse the order of the quantifiers and see if it's still true. And regardless of whether it's true or false, we want to see, does it mean the same thing? It could mean something else and also be true. So if you reverse the quantifiers, that says there exists S in the real numbers such that for all R in the real numbers, R plus S equals 0. So let's try to figure out what this one is saying. This one is saying there's some single S. There's some real number S that we can pick ahead of time. So it's 7 or it's 0 or it's -5. There's some S such that no matter what real number I pick, that real number plus the magic S gives 0. So for example, suppose S equals 7 is the one that we think works. If S equals 7 makes this work, that means that you can pick any real number, and if I add it to 7, I get 0. That's definitely false, right? You can't say I can add 7 to any number and get 0. 7 plus 3 is not 0, for example. If I pick some other number S here, like -5, is it true that if S is -5, then I can pick any real number and add it to -5, get 0? No. It's true for some real number, but it's definitely not true for all of them. So this is like saying, let me repeat it one more time. This expression says there's some magic real number S that if I add it to any real number, it gives 0. And hopefully you understand, like you have some intuition about why that's false. So that's a false statement. The first one says, if you give me any real number, I can give you something that cancels it out to 0. But the second one says, I'm going to give you some magic number that no matter what you add to it, you always get 0. And that's a very different statement. Any questions? The people in the Teams chat, can you let me know if you're hearing me okay or if it's still hard to hear? Now, one caveat of the saying that order matters is that in these cases that we saw, the difference was we had a for all and there exists, and we swapped them, and that made a difference. If you have a bunch of quantifiers that are all the same, then that order doesn't matter. So if the quantifiers are all the same, then the order can be switched. Then the order doesn't matter. So for example, if we had something that was like for all x in the real numbers, for all y in the real numbers, something, just say a predicate p of x, y, that's going to be the same as if we swapped the order because they're the same. They're both for all. Any questions? So we talked a little bit on last class in 1.4 about negating and how you can negate one of these quantified predicates by moving the negation sign inside. You keep moving it in and in and in until it's stuck all the way on the predicate. And every time that negation passes over a quantifier, it swaps it, either from for all to there exists or from there exists to for all. So let's do one more example with this statement that we had before. We're going to take this one and negate it. So this is a true statement. We're going to negate it and get a false statement. But it's a good example for how we negate when we have multiple quantifiers like this. So we already wrote down the rules. I'm not going to write them again, but we take that negation, we move it inward step by step. So if we're going to negate that quantified predicate, which was for all r in the real numbers, there exists s in the real numbers such that r plus s equals 0. You can probably do this in your head once you've done a couple of examples, but at first it's probably useful to write out step by step. So in that first step, we're going to take the negation and move it past the first quantifier. So when we do that, this is logically equivalent to there exists a real number r, because it's moved over, so it swapped from for all to there exists. And then the negation of everything else. So this was one step. It passed over once, and now the negation is attached to everything inside. Now we'll do one more step. The negation will pass one more step inward over the second quantifier. That said, there exists, so it becomes for all. And now the negation is stuck on the whole predicate, so it moved inward one more step. But this is a predicate that's easy to negate. If the predicate says something is equal to 0, the negation is just what? What is the logical opposite of r plus s equals 0? Yeah. Yeah, r plus s does not equal 0. So our last step is to simplify that. And we end up with the quantified predicate that I'm writing here. We'll read it in English in a second. So if we were to translate this to English, this would say, there exists a real number r such that for all real numbers s, for all real numbers s, r plus s is not 0. And I want to go back and look at the original version. I guess we have it right here. And I want us to think about why that's the negation, because it's really important that not just that you can do all the symbolic manipulation and get the answer, but that when you say them both to yourself, you can kind of feel like, oh yes, it makes sense that this is the opposite of that. So this one, remember, one way I explained it was that you could give me any real number r, and I'll give you back some number s that adds up to 0 with your number. So you're like challenging me with an r, and I'm responding with an s that cancels it out to 0. And we said that was true. I could do that. And we know I could do it because I could always just give you back the negative of what you gave me. So the negation should be false because the original statement's true. So the negation says there's some magic real number r that no matter what I add to it, I can never make it 0. So that would be like if you thought the original statement was wrong, how would you try to justify it to me? You would try to come up with some very tricky number r that you give me, and then I'm unable to give you back a number that cancels it. So this would say there's some magic r that you can give me that no matter what I try to give you back, it won't cancel. It won't add up to 0. So this is like the logical opposite. If you thought the original statement was wrong, thought this was wrong, you would try to prove it to me by giving me a number that I can't add something to it and give 0. The more you work with these examples in the suggested homework and on quizzes and things like that, the more comfortable you will be. After a while, especially by the end of the course, these will seem totally trivial and easy to you, but it just takes that practice. Any questions? The other thing I'll say about 1.4 is that the book is really good about this section. It's long, but it has a ton of examples. So if you haven't seen enough examples here in lecture to really make it make sense, I recommend you look at examples in the book too. Okay, so we're going to move on to 1.5. If there are no questions, no questions in the team chat so far. Section 1.5 is the last section in chapter 1 that we're going to do, and it's called implications. So just like we learned in 1.3 how we could take two statements P and Q and turn them into one bigger statement P and Q, or P or Q, implications are kind of the same thing. They let us take two statements and join them together in a certain way to make one bigger statement. So let's start by just defining what an implication is. Let P and Q be statements. So we've got these two statements. Then, if we try to combine them into one bigger statement that says, if P, then Q, or let me phrase this in a way with more words, just so that we see it at the beginning. We're not usually going to write it like this. You could also write this, if P is true, then Q is true. That's what we're really saying. That's kind of implicit. This is abbreviated with the following symbol, P, right arrow, Q. So whenever you see this, which is probably a symbol that you've seen somewhere in math before, this tells you that really what we're saying is if P is true, then Q is true. This is also written as P implies Q. Implies coming from the word implication. So since this is a new symbol, I'll tell you how to write it in LaTeX. This is just /2, T-O. If you do /implies, you get a double arrow, which is not a symbol that we're using right now. So you should use /2, or you could use /right arrow, is a longer way of writing it, to get the symbol. Okay, so I think I started a sentence but still haven't finished it yet in the notes. This whole construct, if P is true, then Q is true, this is called an implication. And one thing that I want to point out is that an implication is itself a new statement built from P and Q. And since it's a new statement, it's either true or false. All statements are either true or false. So if this is a statement, then it's either true or false. Now, implications are kind of tricky things because we have a little bit of English ambiguity again. In English, if you say something like, if P is true, then Q is true, but you fill in something in English for P and Q, you're kind of saying something more than the math is saying. If you say that in English, like, if your mom tells you, if you don't clean your room, then you can't go out tonight, that's implying an actual cause and effect, that one thing is causing the other thing. In math, we're not always implying a cause and effect. It may be true, but we're not necessarily saying that P causes Q to be true. So keep that in mind as we go through examples, and I'll repeat it towards the end. But that's an important thing that can trip people up sometimes. Let's see an example. I guess let me stop and say, are there any questions before we do an example? Okay, so let's start with an English example. Let P be the statement. You live in Milwaukee. And let Q be the statement. You live in Wisconsin. So although we haven't really actually defined what it means for an implication to be true, Right, I said P implies Q is a new statement, so it's either true or false, but I didn't tell you how to determine that. But even though I haven't told you that, if I write some implications about these statements, you'll probably have a pretty good guess for whether those implications are true or false. So first, let's ask about P implies Q. So is P implies Q a true statement or a false statement? Before I get your input, I want to write it out in English. So one way to think about P implies Q that we wrote all the way up at the top is if P, then Q. So let's write it out this way, where P is going to be you live in Milwaukee, and Q is going to be you live in Wisconsin. And here's what this says. It says if you live in Milwaukee, then you live in Wisconsin. So this you live in Milwaukee, that's the P, and you live in Wisconsin, that's the Q. So do we think this is true or false? I want to let you think about it for a little bit. I'm gonna ask for your hands in a second, and people in the chat, if you feel like it, can either answer true or false. If you live in Milwaukee, then you live in Wisconsin. So raise your hand if you think that's true. Raise your hand if you think that's false. Raise your hand if you didn't feel like raising your hand. There we go. So now everybody's raised their hand. This is true. So and I don't need to explain to you probably why it's true. It makes sense to you. If you live in Milwaukee, then you have to live in Wisconsin because Milwaukee's inside of Wisconsin. So in this case, P implies Q is a true statement. Let's look at the reverse though. Q implies P. Q implies P says if you live in Wisconsin, then you live in Milwaukee. So all we've done is change where P and Q are. We swapped them. And if we remember back to our and ors, we had a rule that we called commutativity that said if I swap P and Q with and, or swap them with or, that means the same thing. But do you guys think this is true or false? Yeah, I heard somebody say false. Why do you think this is false? Yeah, Tony. Yeah, so Tony's example was you could live in Madison. If you live in Madison, then it's true that you live in Wisconsin, but it's not true that you live in Milwaukee. So even though I haven't formally told you what it means for an implication to be true or false, you understand on some intuitive level that this one is false. So what we're seeing here is that order matters. Any questions so far? Okay. I'm still not going to tell you exactly when an implication is true or false, but instead we'll do a math example, and then we'll come back to our real formal definition. A lot of times that we use implications, most of the time probably, there's going to be predicates and quantifiers involved. And that's just because in math, we're usually stating a theorem about all numbers or there exists a number or something like that. So here's an example of an implication that involves a predicate and a quantifier. Let me write it out in English, and then we'll translate it to math. So the English statement is, for all real numbers x, if x squared minus x equals 6, then x equals 3. I'm not claiming that this is true, but it certainly looks kind of like an implication. At least it has an implication inside. This part here is an implication, if something, then something. But that implication involves a variable. And if you have a variable, you need to quantify the variable by having something in front. So this is our for all quantifier for that variable. So the way this looks in math is for all x in the real numbers. That's our quantifier. And then our implication, I'm going to put in big square brackets just so that you can see it, kind of like big parentheses. If x squared minus x equals 6, then x equals 3. You don't need to put as many parentheses as I do, but I just think it makes it more clear where the statements stop and start. So again, this says if this, then this. Does anybody want to take a stab if this is a true or a false statement? Let me see if somebody who hasn't answered me yet today wants to give it a shot. For all real numbers x, if this is true, then this is true. Yeah. Okay, we have a vote for true. Yeah. We have a vote for false. Okay, I love when we disagree because it means that we can figure out which one's right, and at least one person has learned something. I've always told you guys, and this is true, my favorite answers that you give me are the wrong answers because it helps me figure out what you're understanding and what you're not. So I like the wrong answers, but I didn't say which one is wrong. So maybe let's take a little vote, and if you don't know, it's fine to not raise your hand. Or raise your hand if you think it's true. Okay, we've got a couple votes there. We've got one vote for true in the chat too. Raise your hand if you think it's false. We've got maybe one or two more votes for false than we had for true. Okay, so my answer is that this is false. And let me try to justify it to you, and then we'll see if you agree. So we're saying if x, whatever x we pick, for all x values, if it makes this true, then it has to make this true. And if you think about it in reverse, then it does seem like it should be true, because if you plug in 3, then you get 9 minus 3 is 6. But what this is really saying is that if this first statement is true, the only way that could happen is if x is 3. But I think there's another solution. If we think about maybe factoring this, we can factor this as x times x minus 1 equals 6. 3 is going to work here, but what else is going to work? Yeah. -2 also works. You might have to move the 6 over and do the quadratic equation or factor, whichever way you learned in pre-calculus. But there's actually 2 different x values that make this true. So it's not necessarily true that if x squared minus x is 6, then x equals 3, because it could also be that x is -2. So we're kind of honing in on what makes an implication true or false. The problem here is that x equals -2, x equals -2 makes this part true, but that part false. Hoping you guys have some questions at this point, because this is where it's tough for me to figure out how much you're following, how much you're not, especially when you're 50 feet away and have masks on. So I'll repeat it again while you're thinking if you have questions. The reason this is false, is that it's not true that anything that makes this true also makes this true. Because we found this -2, which makes the hypothesis, that's what we're going to call this eventually, the hypothesis, true, but it makes the conclusion false. Now let's flip it around like we did with the last example. If we just swap the P and the Q, then what we get is for all x in the real numbers, if x equals 3, then x squared minus x equals 6. Now this is a true statement, unlike the last one. So here's another example where changing the order matters. This one says, if I know x's value from the very beginning, 3, then is it true that when I do this calculation, I get 6? And it is. We saw that last time. 3 squared is 9. 9 minus 3 is 6. So this one, we are kind of assuming, we'll talk more about that later, we're assuming x equals 3. And we're asking, does that imply that x squared minus x equals 6? And this one is more straightforward. It's just yes, because you plug it in, and that's what you get. Whereas the first one, we were assuming something more implicit. We were assuming x squared minus x equals 6 and asking, does that imply x equals 3? And what we saw is the answer is not necessarily. It could be 3, but it doesn't have to be 3 because it could also be negative 2. Any questions? Okay, so now we're finally going to talk about an actual definition about if I just give you P implies Q, what values of P, true or false, and what values of Q, true or false, make P implies Q, true or false. So in the end, we're just going to write a little truth table, just like we did for P and Q and P or Q. So that's what we're going to answer now, is how do we determine whether P implies Q is a true statement or a false statement. So let me write P implies Q in English one more time, but using a lot of extra words to drive a point home. So here's how I'm going to phrase it this time. If P is true, then Q must be true. If P is true, then Q must be true. So this is telling us something if P is true. If P is true, Q must be true. But if P is false, this is not making any restriction whatsoever. If P is false, we don't care about Q. Because we didn't say something like if Q is false, then Q. Sorry, let me start over. We didn't say something like if P is false, then Q must also be false. We didn't say that. That would be a different implication. All the implication says is if it's true, if P is true, Q must be true. And so if P is false, we don't care. Q could be true or false, we don't care. So what that means is that the only way this goes wrong is if P is true, but Q is false. This is the only situation in which an implication P implies Q has value false. Because if P is false, then nothing could go wrong because we don't care about Q. The only thing that could go wrong is if the hypothesis is true and then the conclusion is false, because that violates this. That's the only combination that violates this English phrase, if P is true, then Q must be true. So let me rephrase that one more way. P implies Q is false when P is true and Q is false. Any questions? Yeah. Yeah, the question was, if P is false, does that make the implication P implies Q a true statement, taken as a whole? And the answer is yes. And that's where this can feel a little bit different from how we use this in English. And this is where that, I told you in English, there's kind of like a cause and effect implicit thing going on when you say something implies something, but we don't mean that in math. So for example, let me form, I think I even have this example on the next page, but since you asked, let me just do it now. If I formed an implication that was like, if the moon is made of cheese, then I am 6 feet tall. So I'm not 6 feet tall. So, and the moon is not made of cheese. So this is a false implies false. This is a true implication. The whole implication is true. And that feels weird at first. Obviously, if you said this in English, it doesn't make any sense. These two things are unrelated. Why would you say them in the same sentence? If the moon is made of cheese, then I am 6 feet tall. Obviously, whether or not the moon is made of cheese has no bearing on how tall I am. But in math, this is considered a true implication because the moment the hypothesis is false, we don't care about whether the conclusion is true or false. So once again, this does feel strange at first, but we'll see an example later in 1.5, probably not today, so probably not till Monday, where it will make perfect sense why we think about it this way. The idea, though, is that we're thinking about having a hypothesis and drawing a conclusion. And so, like, if you're thinking like a scientist, you're saying, whenever my hypothesis is true, I'm claiming my conclusion is also true. And then you do a bunch of scientific measurements or something, and you want to say, was I right? Well, you're right if, whenever your hypothesis was true, your conclusion was also true. You might have some observations where your hypothesis didn't hold. You don't care what happens there. They're not going to validate or invalidate your conclusion. If you have a hypothesis, and the question is, when it's true, is my conclusion also true? Okay. So what I want to do now is draw a little truth table. Just like we drew little truth tables for and or, we can do the same thing here. So we've got P, we need 4 rows, Q. We've got our values. So P, we write true, true, false, false. And Q, we write true, false, true, false. And so what we said, let's scroll up for a minute here. We said P implies Q is false when P is true and Q is false. And then I guess implicitly we're saying P implies Q is true in all other cases. So if we go down to our truth table, P implies Q is false when P is true and Q is false. That's this row right here. So in this row, P implies Q is false. And in the other 3 rows, it's true. So let's think about how that relates to what we've been saying. In this first row here, that's a true statement implies a true statement. That's the one that makes the most sense to us. Something true implies something true. That makes a true implication. Then we've got the case which is false, where your hypothesis was true, but your conclusion was false. That's specifically what we want to avoid. And then these last 2 cases here, these are the ones where your hypothesis was false, and so we didn't care about whether the conclusion was true or false. The moment the hypothesis is false, the implication is going to be true. Any questions? Yeah. You're asking about the second row? Yeah. So the question was about the second row, and so let me repeat it. I think this will answer your question. The reason this is false is because it falls into the exactly bad case that we mentioned above. P implies Q is false when P is true and Q is false. That's because the whole point of an implication is that if the first thing is true, the second thing better be true. That's kind of what we're saying. So if the first thing is false, then we don't care about what happens with the second thing. But if the first thing is true and the second thing is false, that's exactly the one bad case we want to avoid. So that's the row where the implication is false. Does that make sense? And so if we look at the kind of silly example that I gave you, if the moon is made of cheese, then I am 6 feet tall. That's this fourth row here. The hypothesis is false, the conclusion is false, but the implication is true because anytime the hypothesis is false, we don't care about the conclusion. Yeah. Yeah, so the question was, can I explain why the implication is true if the hypothesis is false? So you're kind of asking, like, why do we even define it this way in the first place, right? Because that's really just a matter of how you define the symbols. So why are we defining it this way? And I'm going to not answer that question until we get a little further, probably on Monday, where I can do some examples that I hope will make that clear. But the quick answer is that we use implications when we're stating theorems. So like, let me go back up here. Let's think about this example for a second. And suppose that I had said instead, if this is true, then x equals -2 or x equals 3. Suppose that I fixed it like that. So now it's a true implication. We want this to be a true implication. That means whenever the first thing is satisfied, we want the second thing to be satisfied. And it's definitely true because of the little algebra that we did here, that when the first thing is true, the second thing is also true. But, and so you probably agree that this should now be a true statement, right? What if I said, well, what about x equals 0? You would say x equals 0 doesn't satisfy my hypothesis, so it doesn't break my theorem. Right? If you come up and you say, well, what about an x value that doesn't make this true? You don't want that to invalidate your theorem. Your theorem is specifically saying, when this is true, this conclusion is true. And if you give me an x value that makes this not true, that's fine. That doesn't break my theorem or break my fact. So we'll see more examples like this on Monday, but that's kind of the idea behind it. Okay, I got 2 minutes left, so I want to say one last thing about this truth table here. So we've got this truth table. It turns out that you don't really need a new symbol for this idea. Here is a different way of combining P and Q that give me the same thing. It's going to look strange at first, but yeah. Yes. Yeah, so the question was, could he predict what I was going to say? And you said Q or not P. Let me just change the order, because I just like when the P comes first, I guess. Yeah, so what is the truth table for this expression? Well, in the first row, Q is true, and this is an OR, so that makes it true. In the second row, it's false, because P is true, that means this is false, and Q is false. And in the third and fourth rows, P is false, so not P is true. And that makes the whole thing true. So this is the same thing. And that's telling us that this new symbol we defined, it's a useful symbol because it's nice and concise, but really it's logically equivalent, it's logically equivalent to something we could have said earlier. And this is not just like a coincidence. This is because if you think about not P or Q, it should make some sense to you why this is what we've been saying all along. We said our implication is true when the hypothesis is true, the conclusion better be true. And if the hypothesis is false, we don't care. That's what this says. It says, if the hypothesis is false, my whole statement's true, my whole implication. On the other hand, if it's true, I need Q to be true as well. So these are completely the same, and sometimes this is a nicer way to think about it. So before you leave, let me just check, are there any questions? Okay, so when I get back to my office a little bit later, I'm going to pick some suggested homework that covers the material in 1.5 that we've covered so far, and everything up to this is fair game for the exam on Friday. Feel free to email me if you have any questions, and if not, I'll see you on Friday.